Imagine a colossal realm stretching across more than 70% of our planet's surface, its boundaries defined not by continents or borders, but by the ceaseless movement of water. This immense domain, the deep ocean, remains one of Earth's least explored frontiers, its secrets more veiled than those of the farthest planets in our solar system. Beneath the shimmering surface lies a hidden expanse, layered with gradients of light and temperature, where the familiar world above gives way to an environment governed by pressure, darkness, and the slow passage of time. The deep ocean is a realm of perpetual night, where sunlight cannot penetrate, and the only illumination comes from the faint, ghostly glow of bioluminescent life. Here, silence reigns, broken only by the distant rumble of shifting tectonic plates or the subtle movement of unseen creatures. Life in these depths is shaped by relentless extremes. Organisms display astonishing forms and behaviors, each a direct response to the crushing cold, immense pressure, and scarcity of food. Every adaptation is a testament to survival in a world where energy is precious and danger is ever present. The inhabitants of the deep ocean are masterpieces of evolutionary engineering, their bodies streamlined for efficiency, their metabolisms slowed to conserve energy, and their senses finely tuned to detect the faintest signals in the darkness. Bioluminescence is a universal language in the deep, with organisms emitting intricate patterns of blue and green light to attract mates, confuse predators, or lure unsuspecting prey. These living lanterns transform the darkness into a shifting tapestry of color and movement. As one descends from the sunlit shallows, the transformation is immediate and profound. Colors vanish, replaced by a monochrome world where only the faintest traces of light remain, and the water itself seems to absorb all warmth and sound. The vibrant palette of the surface dissolves into a muted twilight, then surrenders to a blackness so complete it feels physical, a darkness that envelops everything, broken only by the occasional pulse of living light. This is the midnight zone, beginning at depths of 1,000 meters, where sunlight is extinguished entirely. Here the pressure is immense, and the only illumination comes from the bioluminescent signals of the creatures that call this place home. Temperatures in the deep ocean hover just above freezing, creating a world where chemical reactions slow dramatically. Organisms here have evolved anti-freeze proteins and specialized enzymes to function in the relentless cold. The pressure increases by 1 atmosphere every 10 meters, reaching over 1,000 times the surface pressure in the deepest trenches. Only creatures with flexible, pressure-resistant bodies can survive these crushing forces. Despite these harsh conditions, life flourishes in astonishing diversity. Each organism is exquisitely adapted to its niche, from slow-moving scavengers to agile predators, all perfectly suited to the abyssal environment. The bizarre forms and haunting silhouettes of deep-sea creatures are not the stuff of nightmares, but ingenious evolutionary solutions, each feature a response to the unique challenges of the deep. Oversized jaws, luminous lures, and translucent bodies are specialized adaptations, enabling predators to ambush prey, attract mates, or remain invisible in the darkness. Some species have evolved enormous, light-sensitive eyes, capable of detecting the faintest glimmer of bioluminescence or the silhouette of prey passing overhead. Others have dispensed with vision entirely, relying instead on acute senses of smell, vibration, or electric fields to navigate, locate food, and avoid predators in the pitch-black environment. Gaping mouths lined with needle-like teeth allow predators to seize and consume prey of nearly any size, ensuring that no rare feeding opportunity is wasted in this food-scarce world. Many deep-sea inhabitants possess gelatinous, nearly transparent bodies, their tissues adapted to withstand immense pressure, minimize energy expenditure, and remain undetected by both predators and prey. Patience is a vital survival strategy. Many predators remain motionless for days or even weeks, conserving energy until the rare moment when a potential meal drifts within striking distance. The deep ocean is a dynamic landscape, shaped by shifting currents, hydrothermal vents, and chemical gradients. Around these vents, entire ecosystems thrive, fueled not by sunlight, but by the chemical energy released from the Earth's interior. New species are continually discovered in these depths, each unveiling novel adaptations. Some glow with internal light, others are armored with mineralized plates, and some survive entirely on chemical reactions with symbiotic bacteria. Isolated ecosystems flourish around volcanic vents and cold seeps, where life is sustained by chemosynthesis. Organisms convert chemicals like hydrogen sulfide and methane into energy, forming the foundation of complex food webs. Evolution in the deep ocean is a relentless force, driving the emergence of creatures with antifreeze proteins to prevent ice formation, expandable stomachs for unpredictable meals, and intricate symbiotic relationships with bacteria that enable survival in toxic environments. The deep ocean is not a barren wasteland, but a vibrant, ever-evolving laboratory where nature's most extraordinary experiments unfold. Here, life forms so astonishing and diverse emerge that they challenge our very understanding of what it means to be alive, revealing a world as rich and complex as any found on land. As we plunge into the midnight zone, we cross a threshold into a world of perpetual darkness, where the pressure is so immense it would crush most surface life in an instant. Temperatures hover just above freezing, and the water is so dense with pressure that only the most specialized organisms can endure. In this alien environment, evolution has produced creatures of astonishing form and function, true monsters perfectly engineered for survival in the abyss. The anglerfish is perhaps the most iconic denizen of these depths. The female's bioluminescent lure, a fleshy filament tipped with a glowing bulb, dangles hypnotically in front of her cavernous mouth. This lure is not just a simple appendage, it is a highly specialized organ, home to colonies of symbiotic bacteria that generate light through a process called bioluminescence, a rare phenomenon in the animal kingdom. The anglerfish manipulates her lure with subtle, lifelike movements, imitating the erratic swimming patterns of small prey. The bacteria within the lure are carefully cultivated by the anglerfish, and the light they emit is precisely tuned to the wavelengths that travel farthest in the deep ocean, maximizing the lure's effectiveness in the blackness. In the utter darkness, this faint glow is a siren call to smaller fish and crustaceans, who are drawn in by the promise of an easy meal, unaware of the danger that lurks just beyond the light. When prey ventures close enough, the anglerfish's jaws snap shut with astonishing speed and force. Her mouth is lined with needle-sharp teeth, and her skull is hinged to allow for a rapid upward strike, maximizing the chances of a successful capture. The teeth of the anglerfish are angled inward, forming a perfect trap. Once a victim is inside, escape is impossible. This adaptation is crucial in a habitat where food is scarce, and every meal could be the last for weeks or even months. Another formidable predator of the midnight zone is the stoplight loosejaw, a species of dragonfish. Its body is sleek and muscular, built for sudden bursts of speed. Along its flanks, rows of photophores emit light in a spectrum of colors, including the rare ability to produce red light. The loosejaw's red bioluminescence is a unique adaptation. Most deep-sea creatures are blind to red wavelengths, rendering the loosejaw effectively invisible as it scans the darkness for prey. This evolutionary innovation allows it to hunt undetected, giving it a decisive edge over competitors. Just beneath the dragonfish's eye sits a specialized photophore acting as a focused spotlight. This organ can be rotated and aimed, allowing the dragonfish to illuminate specific areas of the water column, searching for the faint outlines of potential prey while remaining concealed. With this covert illumination, the loosejaw can stalk its quarry with surgical precision. Its jaws, unencumbered by heavy connective tissue, can swing open to an almost unthinkable angle, enabling it to seize and swallow prey nearly as large as itself. The dragonfish's attack is swift and calculated. It aligns its body with the target, then lunges forward, impaling its victim with needle-like teeth before swallowing it whole. The jaw structure is supported by minimal bone, allowing for extreme flexibility. This adaptation is essential for maximizing the size range of available prey, a necessity in a world where food is unpredictable and competition is fierce. Not all inhabitants of the Midnight Zone are active hunters. The giant isopod, a massive crustacean, is a master of scavenging. Its armored exoskeleton protects it from predators and the crushing pressure, while its powerful legs and antennae help it navigate the soft, silty seafloor in search of decaying organic matter. These isopods can grow to over 0.5 meters in length, dwarfing their terrestrial relatives. Their segmented bodies are highly flexible, allowing them to curl into a defensive ball when threatened, and their compound eyes are adapted to detect the faintest glimmers of bioluminescence. When a large carcass, such as a whale, descends from the upper ocean, it becomes a feast for the isopods. They swarm over the remains, using their strong mandibles to tear through flesh and even bone, recycling nutrients back into the ecosystem. During these rare feeding events, isopods consume enormous quantities of food, sometimes to the point where their bodies become distended and movement is nearly impossible. This ability to gorge and store energy is vital for surviving the long, barren stretches between meals. In controlled environments, giant isopods have demonstrated an extraordinary capacity for fasting, surviving for years without food. Their metabolism slows to a crawl, a remarkable adaptation to the unpredictable availability of resources in the deep. The gulper eel, also known as the pelican eel, is a marvel of anatomical specialization. Its most distinctive feature is its enormous, loosely hinged mouth, which can inflate like a balloon to engulf prey of surprising size. This adaptation allows the gulper eel to capitalize on any available food source, from small fish to larger cephalopods. Its stomach is highly elastic, capable of expanding to accommodate meals many times its own volume. The gulper eel's body is elongated and whip-like, tapering to a fine point. At the tip of its tail, a tiny bioluminescent organ glows softly, possibly serving as a lure to attract curious prey within striking distance of its gaping jaws. When a potential meal approaches, the gulper eel rapidly expands its mouth, creating a vacuum that sucks in water and prey alike. This feeding strategy is highly effective in the sparse, unpredictable environment of the deep. Every anatomical feature of Midnight Zone predators is honed for efficiency. Their bodies are streamlined for minimal energy expenditure, and their senses are acutely tuned to detect the faintest signals of life in the darkness. In this world of scarcity, both predators and scavengers have evolved to exploit every opportunity. Their digestive systems are capable of breaking down tough, nutrient-poor material, and their bodies can store energy for extended periods of deprivation. The black swallower is a prime example of extreme adaptation. Its stomach and skin are so elastic that it can ingest prey twice its own length, sometimes resulting in a grotesquely distended body. However, this strategy is not without risk. Overconsumption can lead to fatal ruptures, a testament to the delicate balance of survival in the abyss. The fangtooth, despite its small size, is one of the most fearsome-looking fish in the deep. Its disproportionately large, dagger-like teeth interlock perfectly, and its heavily armored head provides protection from both predators and the immense pressure. The viperfish is another formidable predator, equipped with a row of photophores along its flanks. These light organs can be flashed in complex patterns, luring prey close enough to be impaled by the viperfish's long, hinged fangs, which fold back when the mouth is closed. Cephalopods, too, have evolved to thrive in the Midnight Zone. Deep-sea squids possess elongated, highly flexible arms lined with suckers, and their bodies are adorned with bioluminescent spots used for communication, camouflage, and hunting. The comb jelly, or ctenophore, is a delicate drifter. Its body is nearly transparent, and rows of cilia beat rhythmically, scattering light into shimmering rainbows. This iridescence confuses predators and may also attract prey, making the comb jelly both elusive and effective. Swarms of amphipods, tiny crustaceans, are the unsung recyclers of the deep. They feed on organic debris, known as marine snow, breaking down detritus and forming the foundation of the midnight zone's complex food web. Siphonophores, colonial relatives of jellyfish, can stretch for meters through the water. Their bodies are composed of specialized zooids, each performing a unique function. Some sting, some digest, others provide buoyancy. Together, they form living nets, ensnaring fish and plankton with bioluminescent lures. Symbiotic relationships are common in the midnight zone. Amphipods may ride on jellyfish, gaining protection and access to food scraps, while in return they help keep their hosts free of parasites, creating a delicate balance of mutual benefit. The deep-sea octopus exhibits extraordinary parental care. Females will guard their eggs for years, never leaving their brood, even as they slowly starve. This self-sacrifice ensures that the next generation has the best possible chance of survival in an environment where every life is hard-won. Marine snow, minute particles of decaying matter, drifts endlessly from the upper ocean, providing a constant, if meager, source of nourishment for countless small creatures. This slow rain of organic material is the lifeblood of the midnight zone, sustaining its intricate web of life. Every species in the midnight zone is engaged in a relentless struggle for existence. Each is exquisitely adapted to the darkness, the pressure, and the scarcity that define this realm. These monsters are not merely survivors, they are the ultimate expressions of evolutionary ingenuity, thriving in a world that remains one of Earth's greatest mysteries. In the eternal night of the deep ocean, where sunlight is utterly absent beyond a few hundred meters, life has engineered a remarkable adaptation: bioluminescence. This is not merely a trick of survival, but a sophisticated biochemical process. Within the cells of countless deep-sea organisms, luciferin molecules react with oxygen, a reaction catalyzed by the enzyme luciferase, resulting in the emission of cold, visible light. Unlike the heat-producing light of fire or electricity, bioluminescent light is nearly 100% efficient, generating almost no warmth, a crucial advantage in the frigid, energy-starved depths. Bioluminescence is so prevalent in the deep ocean that it defines the very character of this realm. It is estimated that up to 90% of deep-sea species, from microscopic plankton to giant squid, possess the ability to produce light. This adaptation has arisen independently in dozens of evolutionary lineages, a testament to its profound utility. The diversity of bioluminescent mechanisms is staggering. Some animals possess discrete photophores, specialized organs that can be focused, shuttered, or even rotated, while others have entire tissues or even symbiotic relationships with light-producing bacteria. The palette of bioluminescence is shaped by the physics of water. Blue and green wavelengths, with their shorter frequencies, travel the farthest through seawater, making them the dominant colors in the abyss. Yet, evolution has produced exceptions. The dragonfish, for example, can both emit and detect red light, a wavelength that is quickly absorbed by seawater and invisible to most other deep-sea creatures. This gives the dragonfish a private channel for hunting and communication, undetectable to both prey and rivals. The ecological functions of bioluminescence are as varied as the creatures that wield it. Some, like the flashlight fish, use light to communicate with conspecifics, flashing coded signals to coordinate schooling or attract mates. Siphonophores, colonial relatives of jellyfish, dangle glowing tentacles to lure prey, their bioluminescent displays mimicking the movements of smaller edible organisms. In the perpetual darkness, these glowing signals are the primary means of interaction, replacing vision and color that dominate shallower waters. The anglerfish is perhaps the most iconic bioluminescent predator. Its lure, an extension of the dorsal spine, is tipped with colonies of symbiotic bacteria that emit a steady, ghostly glow. These bacteria are acquired from the environment and maintained in a specialized organ where the anglerfish can regulate the intensity and pattern of light. The lure can be waved, twitched, or pulsed, mimicking the erratic movements of small prey and drawing victims close enough to be engulfed in a single, lightning-fast strike. Defensive uses of bioluminescence are equally sophisticated. The vampire squid, when threatened, ejects a cloud of sticky, glowing mucus, a dazzling spectacle that confuses and distracts predators. This bioluminescent ink can persist for several minutes, providing ample time for escape. Deep-sea shrimp and copepods employ similar tactics, releasing bursts of light to startle attackers or create glowing decoys. Some species can even autotomize glowing body parts, sacrificing a luminous appendage to distract a predator while the main body slips away into the darkness. Camouflage in the deep ocean is a paradoxical art form. The hatchetfish, for instance, uses counter-illumination. Photophores on its belly emit light that matches the faint, downwelling glow from the surface, rendering the fish nearly invisible to predators lurking below. This camouflage is so precise that some species can adjust the intensity and wavelength of their light in real time, responding to subtle changes in ambient illumination caused by passing clouds or drifting debris far above. Some deep-sea fish, like the stoplight loosejaw, have evolved dual photophores, one emitting red light, the other blue. The red photophore is invisible to most prey, allowing the loosejaw to illuminate and hunt with surgical precision, while the blue photophore can be used for communication or to attract mates. This dual system is a rare example of evolutionary innovation, granting the loosejaw a unique advantage in the competitive world of the deep. Communication in the deep is a language of light. Certain squid and jellyfish pulse with rhythmic flashes, sending species-specific signals to potential mates or rivals. These displays can be as complex as any bird song or mammalian call, with patterns, frequencies, and intensities that convey information about identity, readiness to mate, or territorial boundaries. Some species even synchronize their flashes in vast, coordinated displays, creating living light shows that ripple through the darkness. Bioluminescence also plays a crucial role in the broader ecosystem. Swarms of ostracods and copepods emit bursts of light when disturbed, creating a sparkling underwater snowfall. These flashes can attract larger predators, setting off a cascade of feeding events, or serve as an early warning system for prey species. In some regions, entire layers of the ocean can glow with the collective light of countless microscopic organisms, a phenomenon known as milky seas, visible even from satellites in orbit. In this world, light is more than illumination. It is currency, weapon, shield, and language. Each flash and glow is a product of millions of years of evolutionary refinement, a survival strategy tailored to the unique challenges of the abyss. The ability to control light, its color, intensity, duration, and pattern, has shaped the behavior, physiology, and even the social structures of deep-sea life. The bioluminescent inhabitants of the deep ocean are not passive curiosities. They are active architects of their environment. Their glowing displays influence predator-prey dynamics, mating systems, and even the vertical migration of entire communities. By generating their own light, these organisms have transformed the deep sea from a realm of perpetual darkness into a living, shifting tapestry of color and movement, a testament to the boundless creativity of evolution. Far beneath the sunlit waves, an immense and ancient realm stretches into perpetual twilight. A domain untouched by the passage of time, and largely unaltered by human hands. This is the deep ocean, a vast, shadowy expanse that stands as the last true wilderness on Earth. Here, the seafloor plunges from the continental shelf into yawning abyssal plains, winding trenches, and towering underwater mountains. The environment is defined by extremes, crushing pressures that would flatten any terrestrial structure, temperatures hovering near freezing, and a darkness so complete that not a single photon from the surface penetrates its depths. Despite centuries of technological progress, less than 5% of this immense domain has been directly observed. The remaining 95% conceals a staggering diversity of habitats, each more alien and enigmatic than the last. The deep ocean is a labyrinth of canyons, ridges, and plains, where the landscape is sculpted by geological forces and the slow accumulation of sediment over millions of years. In the perpetual darkness of the abyssal plains, ghostly bigfin squid drift with their impossibly long, elbowed arms, moving with an eerie grace through the water column. Hadal snailfish, delicate yet resilient, glide through trenches deeper than Mount Everest is tall, their bodies perfectly adapted to withstand pressures that would crush steel. Here, life has evolved in profound isolation, giving rise to forms and behaviors found nowhere else on the planet. Many inhabitants of this realm possess gelatinous, nearly transparent bodies, lacking rigid bones and instead relying on flexible tissues to withstand the immense pressure. Others wield bioluminescence, producing ethereal glows in shades of blue, green, and red. This light is used for a multitude of purposes: to lure unsuspecting prey, to communicate in the darkness, to camouflage against faint glimmers from above, and to startle or evade predators. The deep ocean is a theatre of light and shadow, where survival depends on innovation and adaptation. Unique habitats punctuate the darkness: hydrothermal vents, where superheated, mineral-rich water gushes from the seafloor, create oases of life in an otherwise barren landscape. Here, giant tube worms, clams, and shrimp cluster around black smokers, relying not on sunlight, but on chemosynthetic bacteria that convert toxic chemicals into energy. Cold seeps, brine pools, and methane hydrates foster equally bizarre communities, each ecosystem a testament to life's ability to exploit even the most inhospitable environments. The discovery of thriving organisms in these extreme environments has revolutionized our understanding of life's potential. It suggests that similar ecosystems could exist in the subsurface oceans of distant moons, such as Europa or Enceladus, where sunlight never reaches and energy must be drawn from chemical reactions deep below the ice. Yet, even in these remote and seemingly pristine depths, the influence of the surface world is unmistakable. Microplastics and synthetic fibers have been found inside amphipods nearly 11 kilometers below the surface, carried by ocean currents and settling into the deepest trenches. The presence of these pollutants is a stark reminder that no part of the planet is truly isolated from human activity. The deep ocean is not a world apart, but a vital component of Earth's interconnected systems. Its powerful currents help regulate global climate, distributing heat and nutrients across vast distances. The organisms that inhabit these depths play a crucial role in recycling nutrients, breaking down organic matter, and supporting the resilience of the entire marine biosphere. Each species, from the tiniest amphipod to the largest cephalopod, is a living archive of evolutionary innovation. These organisms are survivors and pioneers, their bodies and behaviors shaped by millions of years of adaptation to the most challenging conditions on Earth. Their unique biochemistry and physiology may hold the keys to new medicines, materials, and insights into the origins and limits of life. The deep sea is a living laboratory where the boundaries of biology are constantly redrawn. Here, organisms endure pressures hundreds of times greater than at the surface, temperatures near freezing, and a scarcity of food. Their adaptations, ranging from pressure-resistant enzymes to slow metabolisms and extraordinary sensory organs, demonstrate the remarkable plasticity of life. The deep ocean is a mosaic of habitats, each supporting life forms found nowhere else. Intricate coral gardens and glass sponge reefs rise from the seafloor, providing shelter for countless species. Shimmering vent fields teem with rare fauna, while the silent plains of the abyss are dotted with starfish, sea cucumbers, and other enigmatic creatures, many of which emit a subtle bioluminescent glow. Survival in this environment demands extraordinary strategies. Predators employ stealth, lures, and even chemical deception to capture prey, while prey species rely on camouflage, rapid escape responses, and the ability to blend seamlessly into the darkness. Many deep-sea organisms form symbiotic partnerships, sharing resources or providing mutual defense in a world where every advantage can mean the difference between life and death. Reproduction and development in the deep ocean are equally remarkable. Some species brood their eggs for years, providing protection in the harshest of environments, while others release larvae that drift for months on deep currents before settling. Ancient lineages, unchanged for millions of years, persist here as living fossils, offering a window into the distant evolutionary past. The ecological significance of the deep ocean cannot be overstated. Its food webs are fueled by marine snow, a continuous rain of organic particles descending from the surface, sustaining life in the darkness. Scavengers and decomposers ensure that every fragment of organic matter is recycled, maintaining the delicate balance of this hidden world and supporting the global cycling of nutrients. The last true wilderness on Earth is not a place of monsters, but of marvels. It is a realm of enduring beauty, resilience, and complexity, a living testament to the creativity of evolution and the interconnectedness of all life. Its secrets remain largely hidden, its wonders deserving of both awe and vigilant protection. As we continue to explore and learn, let us remember that the deep ocean is not merely the planet's final frontier. It is a living legacy, a source of inspiration, and a vital chapter in Earth's ongoing story. The adventure of discovery continues, and with it, our profound responsibility to safeguard this extraordinary wilderness for generations to come. Gap 2s. In the unbroken blackness of the ocean's deepest trenches, evolution unfolds as nature's most audacious experiment, one that has produced life forms as alien as any found on distant planets. Here, the familiar rules of biology are bent and reshaped by the crushing pressure, near freezing temperatures, and total absence of sunlight, forging organisms that defy expectations and challenge our understanding of what life can be. Over countless millennia, deep-sea creatures have diverged from their shallow-water relatives, each lineage sculpted by the relentless demands of the abyss, where water pressure can exceed 1,000 times that at the surface and temperatures hover just above freezing. The result is a living mosaic of adaptations, some so subtle they escape notice, others so dramatic they seem almost fantastical, each one a testament to the ingenuity of evolution. Many deep-sea inhabitants have evolved bodies with minimal skeletal structure, composed largely of gelatinous tissue. This adaptation allows them to withstand immense pressure without the risk of structural collapse, and to conserve energy in a world where food is scarce. The blobfish, for instance, is a marvel of buoyancy control. Its flesh is less dense than water, enabling it to hover effortlessly above the sea floor, conserving precious energy in an environment where every calorie counts. Sensory adaptations in the abyss are equally remarkable, with vision evolving along divergent paths depending on ecological niche. Some species, like the giant squid and certain dragonfishes, possess enormous, ultra-sensitive eyes, capable of detecting the faintest glimmers of bioluminescence, light produced by other organisms as signals, camouflage, or lures. Others, such as the blind cusk eel, have dispensed with vision entirely, evolving heightened senses of touch, vibration, and chemoreception. These adaptations allow them to detect prey, mates, and predators through subtle changes in water movement or chemical gradients. Feeding strategies in the abyss are as diverse as the creatures themselves, shaped by the scarcity and unpredictability of food. The gulper eel, with its expandable jaws and stomach, can engulf prey nearly half its own size, an adaptation that allows it to capitalize on rare feeding opportunities. The anglerfish, meanwhile, wields a bioluminescent lure, an extension of its dorsal spine tipped with glowing bacteria, to attract unsuspecting prey directly into its jaws, a perfect example of evolutionary innovation. The tripod fish stands sentinel on elongated fins, motionless for hours, using delicate sensory filaments to detect vibrations from passing prey, a strategy that conserves energy while maximizing hunting efficiency. Reproduction in the deep sea is a study in ingenuity, with strategies tailored to the vastness and isolation of the abyss. Some species release buoyant eggs that drift upward, allowing larvae to develop in nutrient-rich, shallower waters before descending to the depths as adults, ensuring wide dispersal and increased survival chances. The deep-sea octopus Granelodone bora opacifica demonstrates extraordinary parental investment, brooding its eggs for over 4 years, the longest known brooding period of any animal, guarding them from predators and infection until they hatch. Symbiosis is a recurring theme in the abyss, where partnerships often mean the difference between survival and extinction. At hydrothermal vents, giant tube worms host chemosynthetic bacteria within their tissues. These bacteria convert toxic vent chemicals into energy, providing nourishment for the worms in a world devoid of sunlight, a relationship that bypasses photosynthesis entirely. Elsewhere, shrimp and anemones form mutualistic alliances, with shrimp cleaning the anemones and receiving protection from predators in return, exemplifying the complex interdependence that characterizes deep-sea ecosystems. The abyss is also a refuge for ancient lineages, living fossils whose basic forms have persisted for hundreds of millions of years, largely unchanged by time. The coelacanth, once thought extinct, and the giant isopod, a relic of primordial seas, offer a glimpse into evolutionary history, their survival a testament to the effectiveness of ancient adaptations. These survivors illustrate how certain evolutionary solutions, such as slow metabolism, robust exoskeletons, and efficient energy use, can endure for eons in the face of environmental extremes. Every adaptation, whether for movement, feeding, or reproduction, is a finely tuned response to the abyss's unique challenges, honed by relentless natural selection. The evolutionary arms race in the deep ocean is ongoing, driving a continuous cycle of innovation as predators and prey adapt to outwit one another in a world where resources are scarce and competition is fierce. Far from being a graveyard of failed experiments, the deep sea is a vibrant laboratory of evolutionary creativity where life's most extraordinary forms and strategies are put to the ultimate test. Each organism that thrives here is a living record of nature's relentless drive to adapt, endure, and innovate, proof that even in the most forbidding corners of our planet, life finds a way. Far beneath the waves, in a realm untouched by sunlight, the seafloor unfolds as a landscape more alien and dramatic than any terrestrial wilderness. Here, perpetual darkness cloaks a world sculpted by immense geological forces, where every contour and crevice tells a story of Earth's restless interior. The deep ocean is a tapestry of extremes, shaped by the slow collision and separation of tectonic plates. Towering underwater mountains, known as mid-ocean ridges, rise from the abyss, while vast trenches plunge deeper than any canyon on land. Hydrothermal vents, with their billowing plumes, punctuate this landscape, each feature a testament to the planet's ceaseless transformation. The mid-ocean ridges, stretching for over 65,000 kilometers, form the longest mountain chain on Earth. These ridges are the birthplace of new oceanic crust, where molten magma wells up from the mantle, cools, and solidifies, creating a jagged backbone that bisects the ocean basins. As tectonic plates diverge, molten rock surges upward, forging rugged peaks and deep valleys. The relentless movement of these plates generates earthquakes and volcanic eruptions, constantly reshaping the seafloor and giving rise to new geological formations. Along these ridges, hydrothermal vents, aptly named black smokers, erupt with jets of superheated, mineral-laden water. Temperatures here can exceed 400 degrees Celsius, yet the surrounding water remains near freezing, creating stark thermal gradients. Minerals dissolved in the vent fluids rapidly precipitate upon contact with cold seawater, constructing towering chimneys of metal sulfides. Some of these mineral spires reach heights of over 15 meters, forming intricate, ever-changing structures that rise from the seafloor like underwater cathedrals. These mineral towers become the foundation for unique ecosystems, where chemosynthetic bacteria harness chemical energy from vent fluids, supporting dense communities of tube worms, clams, and crustaceans. Life here thrives in complete darkness, independent of the sun, relying on the chemistry of the Earth itself. In stark contrast, the ocean floor also descends into immense trenches, vast chasms formed by the subduction of tectonic plates. These trenches are among the most mysterious and least explored regions on the planet. The Mariana Trench, the deepest known point on Earth, plunges nearly 11,000 meters into the abyss. Its steep, shadowy walls are sculpted by immense pressure and geological upheaval, creating an environment of perpetual twilight and crushing force. At these depths, the pressure exceeds 1,000 times that at the surface, and temperatures hover just above freezing. Only the most specialized organisms can survive here, their bodies adapted to withstand the crushing weight and frigid darkness. Trenches are carved by subduction zones, where one tectonic plate is forced beneath another. This process not only forms the deepest parts of the ocean, but also triggers powerful earthquakes and volcanic activity, perpetually altering the seafloor's topography. Rising from the abyssal plains are seamounts, underwater volcanoes that can soar thousands of meters above the surrounding seafloor. Some break the surface to form islands, while others remain submerged, isolated havens of rock and coral in the vast deep. These geological giants disrupt ocean currents, causing nutrient-rich waters to upwell from the depths. This upwelling transforms seamounts into hotspots of productivity, attracting a remarkable diversity of marine life. The slopes and summits of seamounts provide critical habitat for countless species, from ancient sponges filtering the water to migratory fish seeking refuge and food. Each seamount is a microcosm of deep-sea biodiversity. The geology of the deep ocean is in perpetual flux. Earthquakes ripple along fault lines, new hydrothermal vents burst forth, and fine sediments drift slowly across the plains, settling in layers that chronicle the ocean's dynamic past. Scattered across the abyssal plains, manganese nodules, metallic spheres rich in iron, manganese, and rare elements, grow millimeter by millimeter over millions of years. Their presence reveals the slow, persistent chemical processes at work in the ocean's depths. The sediment blanketing the seafloor is a living archive, each layer capturing traces of volcanic eruptions, shifting currents, and the steady descent of organic matter from the surface. These layers preserve a detailed record of Earth's geological and biological history. Collectively, these geological wonders form the foundation of deep-sea life, shaping habitats and driving the evolution of extraordinary organisms uniquely adapted to this extreme environment. The deep ocean floor is a realm of constant transformation, a silent, ever-changing record of Earth's dynamic forces, waiting to reveal its secrets to those who dare to explore its depths. Beneath the immense pressure and perpetual darkness of the deep ocean, where sunlight never penetrates, life persists through a complex and finely tuned web of interactions. Here, every organism is shaped by scarcity, and survival hinges on extraordinary adaptations and the relentless recycling of energy. Unlike the sunlit surface, where photosynthesis forms the base of the food chain, the deep ocean's energy budget is dictated by the slow, downward drift of organic matter from above and by unique chemical processes at the seafloor. This food web is a tapestry of specialized feeders, opportunistic predators, and patient scavengers, each occupying a niche carved by the ocean's extremes. The primary sustenance for most deep-sea life is marine snow, a continuous shower of organic particles, including dead plankton, mucus, fecal pellets, and fragments of decaying animals and plants. These microscopic fragments, originating from the ocean's productive upper layers, begin a slow descent, transforming as they are colonized by bacteria and tiny invertebrates. Fish scales, crustacean shells, and fecal pellets join this rain, each particle a miniature ecosystem teeming with microbial life. As this detritus settles on the abyssal plain, it forms a thin, patchy layer that is quickly exploited by benthic organisms, sea cucumbers, brittle stars, and polychaete worms, each adapted to extract every possible calorie from the sparse supply. Some creatures, like the deposit-feeding sea cucumber, ingest sediment wholesale, digesting the organic matter and excreting the rest, while others, such as certain amphipods, meticulously pick through the debris for richer morsels. In stark contrast, hydrothermal vents and cold seeps introduce a second, independent energy source, chemosynthesis. Here, chemosynthetic bacteria thrive on hydrogen sulfide and methane, converting these chemicals into organic compounds through metabolic pathways entirely independent of sunlight. These bacteria form dense mats or live symbiotically within the tissues of vent fauna, giant tube worms, clams, and mussels, providing them with nourishment in exchange for access to chemical-rich fluids. The result is a thriving, self-contained ecosystem where crabs, shrimp, and predatory fish exploit the abundance, and the rules of the food web are dictated by chemistry rather than sunlight. Predator-prey dynamics in the deep are shaped by darkness and scarcity. Many predators rely on stealth, bioluminescence, or highly sensitive sensory organs to locate prey. The gulper eel, for example, can unhinge its jaws and inflate its stomach, allowing it to swallow prey nearly half its own length, an adaptation to unpredictable meals. The anglerfish wields a luminous lure, a specialized dorsal spine tipped with glowing bacteria to mimic the faint glimmer of falling detritus and attract unsuspecting prey within striking distance. The vampire squid, a relic of ancient lineages, is uniquely adapted to low-oxygen waters. It floats passively, conserving energy, and feeds on marine snow and drifting detritus rather than hunting live prey. When it senses vibrations, it unfurls its cloak-like webbed arms, trapping organic particles and tiny animals in a sticky mucus coating. Scavengers are the ultimate recyclers, ensuring that no resource is wasted. They are quick to exploit any sudden windfall, such as a large carcass descending from above. When a whale dies and sinks, its body becomes a temporary oasis. Hagfish burrow into the flesh, amphipods swarm over the remains, and a succession of scavengers arrives in waves, each specializing in different tissues. Sleeper sharks, with their powerful jaws, strip away muscle and fat, while smaller crustaceans and worms consume the softer tissues and connective matter. As the feast wanes, bacteria and bone-eating worms, such as Ossidax, colonize the skeleton, breaking down bone lipids and releasing nutrients that will sustain microbial communities for years. The decomposition process is slow and methodical, aided by sluggish currents that distribute dissolved nutrients across the seafloor, fueling new growth in an otherwise barren landscape. Microbes are the unseen engines of this ecosystem, breaking down even the most resistant organic molecules and recycling them into forms usable by other organisms. Some nutrients are swept upward by turbulent currents, nourishing mid-water animals like siphonophores, ctenophores, and gelatinous zooplankton, which in turn become prey for larger predators. Other nutrients become trapped in deep sediments, where they may remain for centuries, subtly influencing the chemical makeup of the ocean and supporting slow-growing, long-lived species. In this world of scarcity, every scrap of organic matter is contested and competition is fierce. Many animals have evolved slow metabolisms, allowing them to survive long periods between meals. The deep ocean food web is a marvel of interconnectedness and efficiency. From the tiniest microbe to the largest scavenger, every organism plays a role in the cycling of matter and energy, ensuring that nothing is wasted. Here, life and death are inextricably linked in a continuous cycle. The struggle for existence is both harsh and awe-inspiring, a testament to the ingenuity of evolution in Earth's most enigmatic and unforgiving realm. For millions of years, the deep ocean has existed in near isolation, untouched, unspoiled, and governed by ancient, relentless forces. Its vast plains, towering seamounts, and abyssal trenches have remained shrouded in perpetual darkness, their ecosystems evolving in delicate balance, far removed from the turbulence of the surface world. Yet today, even these remote depths are no longer immune to the far-reaching influence of human activity. The evidence of our presence now lies scattered across the abyss, from the faint glow of submersible lights to the silent descent of foreign objects, each marking a subtle but profound intrusion into this ancient realm. Recent scientific expeditions, equipped with advanced submersibles and remotely operated vehicles, have begun to systematically map and monitor the deep. These missions have revealed not only the wonders of the abyss, but also a growing catalogue of disturbances, shifts in water chemistry, altered current patterns, and the unmistakable fingerprints of human industry. Among the most profound threats is the relentless advance of climate change. The deep ocean, once buffered from surface fluctuations, is now experiencing subtle but significant shifts in temperature and circulation. Ocean currents, which once delivered life-sustaining oxygen and nutrients to the depths, are being altered by warming surface waters and changing wind patterns. As global temperatures rise, the oceans absorb vast quantities of heat and carbon dioxide. This process not only warms the upper layers but also drives chemical changes that ripple downward. The thermocline, the boundary between warm surface water and the cold abyss, becomes more pronounced, impeding the vertical mixing that once replenished deep waters with oxygen and nutrients. As a result, oxygen-rich currents sink more slowly, and vast oxygen minimum zones expand across the deep. In these hypoxic regions, marine life is forced to adapt, migrate, or perish. Entire communities of organisms, some of which have persisted for millions of years, now face the threat of suffocation in their own habitat. Ocean acidification, driven by the relentless absorption of carbon dioxide, is another invisible but devastating force. The increased acidity weakens the calcium carbonate structures that form the skeletons and shells of deep-sea corals, mollusks, and plankton. These organisms, foundational to the deep-sea food web, become more vulnerable to predation and disease, threatening the stability of entire ecosystems. Pollution, once thought to be confined to coastal waters, now permeates the deepest trenches. Plastic debris, ranging from discarded fishing gear to single-use packaging, drifts down through the water column, eventually settling on the ocean floor. These foreign materials accumulate in crevices and on sediment plains, disrupting habitats and introducing toxins into the food chain. Microplastics, nearly invisible to the naked eye, are now ubiquitous in deep-sea sediments. These tiny fragments are ingested by a wide range of organisms, from filter-feeding invertebrates to scavenging amphipods. The ingestion of microplastics can cause physical harm, block digestive tracts, and introduce persistent organic pollutants into the bodies of deep-sea creatures, with consequences that remain poorly understood. Even in the most remote and inaccessible trenches, researchers have detected traces of industrial chemicals, pesticides, and heavy metals. These contaminants, carried by ocean currents and atmospheric deposition, settle into the sediments and bioaccumulate in the tissues of deep-sea organisms. The presence of polychlorinated biphenyls, mercury, and other toxic substances in these isolated environments is a stark testament to the global reach of human pollution. Perhaps the most immediate and tangible threat is the accelerating interest in deep-sea mining. Industrial machinery, designed to extract valuable minerals from the ocean floor, is now being deployed in areas once considered inaccessible. These operations target polymetallic nodules, cobalt-rich crusts, and hydrothermal vent deposits, each supporting unique and fragile biological communities. The ocean floor is scattered with mineral resources, nodules rich in manganese, nickel, and cobalt, as well as crusts containing rare earth elements essential for modern technology. The extraction of these materials involves the removal of vast quantities of sediment and rock, fundamentally altering the physical landscape of the deep. Mining operations generate massive sediment plumes that can drift for kilometers, smothering filter-feeding organisms and clogging the gills of fish and invertebrates. The release of toxic byproducts, including heavy metals and hydrocarbons, further contaminates the water and sediments, with effects that may persist for decades or longer. The scars left by mining, vast barren patches, collapsed habitats, and disrupted microbial communities may take centuries or even millennia to heal. The slow pace of deep-sea recovery means that damage inflicted today could outlast generations, permanently altering the evolutionary trajectory of countless species. Yet amid these mounting challenges, the deep ocean continues to demonstrate remarkable resilience. In undisturbed regions, ancient corals and enigmatic creatures persist, their survival a testament to the enduring strength of life in the abyss. International efforts are underway to establish marine protected areas in the high seas, aiming to shield vulnerable habitats from exploitation. These sanctuaries, guided by rigorous scientific assessment, offer a refuge for species threatened by extraction, pollution, and climate change. Scientists are racing to catalogue the extraordinary diversity of the deep, employing genetic sequencing and advanced imaging to uncover new species and understand their adaptations. This research not only expands our knowledge, but also informs conservation strategies tailored to the unique challenges of the abyss. Cutting-edge technologies, from remotely operated vehicles to environmental DNA sampling, are illuminating the hidden impacts of human activity. These tools enable the detection of subtle changes in ecosystem health, the tracking of pollutant pathways, and the identification of critical habitats in need of protection. The future of the deep ocean now hangs in a delicate balance. The choices made in the coming years regarding resource extraction, pollution control, and habitat protection will determine whether this last great wilderness endures or succumbs to irreversible change. By recognizing the intrinsic value of the deep ocean and acting decisively to mitigate our impact, it is possible to preserve its mysteries and ensure the continued survival of its extraordinary inhabitants for generations to come. Beneath the shadowed waves, where sunlight surrenders to darkness and pressure mounts to crushing extremes, lies a world almost entirely hidden from human eyes. The deep ocean is a realm of perpetual night, where temperatures hover near freezing and the weight of the water above would flatten any unadapted life. Despite advances in submersible technology and remote sensing, only a fraction of this vast domain has been mapped or observed, leaving most of its secrets untouched. Each new discovery seems to deepen the enigma, revealing how little we truly know about the planet's largest habitat. In the absolute silence and darkness, the deep ocean becomes a stage for phenomena that challenge scientific explanation. Acoustic monitoring has captured sounds that defy classification, some so powerful they reverberate across entire ocean basins. The bloop, detected in 1997, was a low-frequency, ultra-loud sound that traveled thousands of kilometers, its origin still a subject of scientific debate. Some hypothesize it was caused by the fracturing of Antarctic ice. Others suggest the grinding of tectonic plates deep beneath the seafloor, while a few entertain the possibility of a colossal, undiscovered animal producing the sound. Other unexplained noises, such as the upsweep and Julia, have been recorded for decades, their spectral signatures distinct, yet their sources elusive. These sounds echo through the labyrinthine corridors of the deep, hinting at geological or biological processes still unknown. The origins of these acoustic mysteries remain shrouded, fueling speculation about the forces at work in the abyss. Visual encounters are equally enigmatic. Submersibles occasionally capture fleeting images of life forms that defy classification. Some appear as translucent spheres, their bodies pulsing with shifting colors produced by bioluminescent proteins. Others resemble drifting veils or gelatinous ribbons, their forms adapted to the crushing pressure and scarcity of food. Elongated, serpentine animals twist through the water, their movements slow and deliberate, conserving energy in a world where every calorie counts. Occasionally, immense shadows drift past the camera, vanishing before their true scale or nature can be determined. These glimpses suggest entire ecosystems thriving in isolation, populated by organisms with adaptations unlike anything seen at the surface. Some creatures possess antifreeze proteins, others generate light to lure prey or communicate, and many have evolved pressure-resistant enzymes to survive where the water is denser than lead. The deep is also a theatre for rare, dramatic events that transform the landscape in moments. Sudden blooms of bioluminescent jellyfish can light up the darkness, their synchronized pulses creating underwater auroras. These displays may be triggered by subtle changes in water chemistry or the presence of predators, but the exact mechanisms remain a mystery. When a whale dies and sinks, its body becomes a rare and vital resource, known as a whale fall. This event supports a succession of specialized scavengers, from giant isopods to bone-eating worms, creating a temporary oasis in the desert of the deep. Among the most bizarre features are brine pools, dense hypersaline lakes that form on the seafloor, their surfaces shimmering like liquid mirrors. These pools are so salty that they are toxic to most marine life, yet some extremophiles thrive at their margins, feeding on chemicals that would be lethal elsewhere. The existence of such life challenges our understanding of biology and expands the possibilities for life in extreme environments, even beyond Earth. Hydrothermal vents and cold seeps further support unique communities, where organisms rely on chemosynthesis rather than sunlight, forming the base of food webs independent of the surface. Each discovery in these alien landscapes raises new questions about adaptation, survival, and the limits of life. What colossal species might still lurk in the unexplored trenches, where pressure is over 1,000 times that at sea level? How do deep-sea animals communicate, hunt, or find mates in a world without sunlight? Do they use light, sound, or chemical signals unknown to science? What triggers the spectacular bioluminescent waves that sweep across the abyssal plains? And what purpose do these displays serve in the ecosystem? The deep ocean remains the planet's final frontier, a place where the boundaries of scientific knowledge are constantly tested and redefined. Here, the interplay of darkness, pressure, and isolation has produced life forms and phenomena that seem almost otherworldly. As robotic explorers and autonomous vehicles venture deeper, each mission uncovers new forms, new sounds, and new puzzles. The greatest mystery may be the sheer scale of what remains unseen. Vast stretches of ocean floor, hidden canyons, and uncharted ecosystems. In the eternal night below, the deep ocean guards its secrets, waiting for the next discovery to illuminate its wonders. To unlock the secrets of the deep, humanity has engineered a suite of specialized machines, each meticulously designed to withstand the ocean's most punishing extremes, pressures that would crush steel, temperatures near freezing, and a darkness so complete that light itself is devoured. Our exploration begins not with human senses, but with the ingenuity of pressure-resistant alloys, syntactic foams, and advanced life support systems, all integrated into submersibles capable of descending to depths exceeding 10,000 meters. Manned submersibles, encased in titanium or specially formulated composite hulls, are engineered to maintain internal atmospheric pressure, allowing sensitive electronics and delicate instruments to function in the crushing abyss. Legendary vessels such as Alvin and Trieste are equipped with multi-layered acrylic viewports, robotic manipulators with sub-millimeter precision, and modular payload bays for deploying scientific instruments directly onto the sea floor. Within these pressurized environments, high-sensitivity cameras and robotic arms collect mineral samples, probe hydrothermal vents, and document bioluminescent life forms in their native habitats, all while maintaining a sterile barrier against contamination. Despite these advances, vast regions of the abyss remain beyond the reach of direct human intervention, demanding ever more sophisticated remote technologies. Remotely operated vehicles, or ROVs, serve as the vanguard of deep-sea exploration, tethered to surface vessels by fiber-optic cables that transmit power and high-bandwidth data streams across kilometers of water. Outfitted with ultra-bright LED arrays, 4K and hyperspectral cameras, and real-time telemetry, ROVs relay detailed imagery and environmental data to operators on the surface, enabling precise navigation and manipulation in total darkness. Their dexterous manipulator arms, often equipped with force feedback controls, delicately harvest fragile organisms and extract geological cores, while integrated sensor suites analyze water chemistry, detect trace gases, and monitor microbe populations in situ. Advanced ROVs employ multi-beam sonar and structured light scanning to generate high-resolution, three-dimensional maps of the seafloor, revealing previously unseen geological features and habitats. For regions too hazardous or remote for tethered vehicles, autonomous underwater vehicles, or AUVs, are deployed, untethered, self-guided, and programmed to execute complex survey missions over vast distances. These robotic explorers utilize inertial navigation, Doppler velocity logs, and acoustic positioning systems to traverse intricate underwater landscapes, avoiding obstacles and adapting to unpredictable currents. AUVs are equipped with a suite of environmental sensors measuring salinity, dissolved oxygen, current velocity, and magnetic anomalies, while simultaneously mapping seafloor topography with sub-meter accuracy. Their silent propulsion systems and extended battery life enable them to penetrate narrow crevices, deep canyons, and isolated hydrothermal fields, gathering ecological and geological data from locations previously inaccessible to science. Across the ocean's depths, networks of autonomous sensors, anchored to moorings or drifting with the abyssal currents, form a persistent, distributed observatory, continuously recording environmental variables over months or even years. These instruments, shielded against corrosion and biofouling, log temperature gradients, acoustic signatures, and subtle shifts in biogeochemical cycles, providing time series data essential for modeling ocean dynamics and ecosystem change. From hydrothermal vent fields to the vast abyssal plains, specialized monitoring stations track seismic activity, vent chemistry, and microbial community shifts, offering unprecedented insight into the planet's most extreme environments. Collectively, these technological innovations have revolutionized deep-sea science, enabling systematic exploration, long-term monitoring, and rapid response to transient phenomena such as volcanic eruptions or methane seeps. Through relentless innovation and precision engineering, we now illuminate the ocean's most enigmatic realms, capturing the unknown and transforming the mysteries of the abyss into data, discovery, and scientific understanding. One mission, one breakthrough, one revelation at a time. Beneath the immense pressure and perpetual darkness of the deep ocean, life has evolved with astonishing ingenuity. Here, every adaptation is a response to scarcity, and survival hinges on strategies that go far beyond brute force or speed. In this extreme environment, symbiosis, mutually beneficial relationships between species, becomes a cornerstone of existence. These alliances are often highly specialized, shaped by millions of years of evolution, to maximize survival in a world where energy is precious and opportunities are rare. One of the most remarkable examples is the partnership between giant tube worms and chemosynthetic bacteria at hydrothermal vents. These vents spew mineral-rich, superheated water, creating isolated oases of life on the otherwise barren sea floor. Tube worms lack mouths, stomachs, or intestines. Instead, their bodies are adapted to house dense populations of bacteria within a specialized organ called the trophosome. These bacteria harness energy from hydrogen sulfide, a toxic chemical abundant in vent fluids, converting it into organic compounds that nourish both themselves and their tube worm hosts. The tube worms, in turn, absorb hydrogen sulfide and oxygen from the water using specialized hemoglobin, delivering these chemicals directly to their bacterial partners. This seamless chemical exchange allows both organisms to thrive in an environment lethal to most forms of life. In the inky blackness far from any vent, the anglerfish demonstrates a different kind of symbiosis, one that illuminates the darkness. The anglerfish's lure, or esker, is colonized by bioluminescent bacteria that emit a cold blue-green glow. These bacteria are highly specialized, unable to survive outside their host, and are passed from one generation of anglerfish to the next. In exchange for a safe habitat and a steady supply of nutrients, the bacteria provide the anglerfish with a light source which is used to lure prey in the pitch-black depths. This bioluminescent beacon is a deadly trap for smaller fish and crustaceans, ensuring both the anglerfish and its microbial partners are sustained in a world where food is scarce. Symbiotic relationships in the abyss also provide protection. Many species seek shelter among the spines, tentacles, or bodies of others, gaining safety from predators in exchange for cleaning or other services. Blind shrimp living near hydrothermal vents form alliances with giant tube anemones. The shrimp, nearly sightless in the darkness, rely on chemical cues and touch to navigate their world. The anemone's stinging tentacles ward off would-be predators, creating a safe haven for the shrimp. In return, the shrimp meticulously clean the anemone, removing parasites and debris that could otherwise harm their host. Even scavengers, often seen as competitors, display remarkable cooperation. When a large food source appears, such as a whale fall, a complex community assembles. The carcass of a whale, once it settles on the seafloor, becomes a hub of activity, supporting a succession of specialized feeders over months or even years. Hagfish and sleeper sharks strip away flesh, while bone-eating worms, known as osedacs, bore into the bones, extracting nutrients with the help of their own symbiotic bacteria. This coordinated breakdown ensures that every part of the carcass is utilized, recycling nutrients into the ecosystem and supporting a diverse array of life. In the deep, where food is unpredictable and often separated by vast distances, such collaborations are essential for survival. The deep ocean is a living mosaic of interdependence, where every organism's fate is intertwined with others, and cooperation is as vital as competition. From the smallest microbe to the largest scavenger, each species has evolved unique adaptations that enable them to participate in these complex networks of survival. In these silent, pressurized depths, symbiotic partnerships are the invisible threads weaving the fabric of the ecosystem, each interaction a finely tuned balance of give and take. Every alliance, every adaptation, stands as a testament to the resilience, complexity, and ingenuity of life at the very frontier of our planet's biosphere. Descending into the deep ocean is an immersion into a realm where the fundamental laws of chemistry and physics are pushed to their limits, sculpting an environment unlike any other on Earth. Here, water is not merely a passive medium, but an active agent. its molecular structure and movement dictating the fate of both geology and biology. The density, viscosity, and unique solvent properties of seawater drive the dissolution and transport of minerals, nutrients, and gases, shaping the very fabric of deep sea ecosystems. Pressure, the most unyielding force in the abyss, increases inexorably with depth, compressing everything in its path. For every 10 meters descended, the hydrostatic pressure rises by 1 atmosphere, resulting in over 1,000 atmospheres at the ocean's greatest depths, enough to collapse unprotected structures and alter the behavior of molecules themselves. In the Mariana Trench and similar abyssal zones, this immense pressure compresses water molecules, reduces gas solubility, and even influences the crystalline structure of minerals, creating a world where only the most specialized adaptations can persist. Deep-sea organisms have evolved remarkable solutions. Their cell membranes are rich in unsaturated fatty acids, maintaining fluidity under compression, while their proteins and enzymes are structurally reinforced to resist denaturation and maintain function at crushing pressures. Even at the microbial level, extremophile bacteria possess cell walls fortified with unique lipids and cross-linked polymers, enabling survival in conditions that would destroy most terrestrial life. Temperature in the deep ocean is another defining parameter, with most regions locked in perpetual cold. Shielded from sunlight, the water temperature stabilizes just above freezing, typically between 2 and 4 degrees Celsius. This frigid environment slows metabolic rates, influences the solubility of gases, and affects the kinetics of chemical reactions, demanding highly efficient biochemical pathways for survival. In stark contrast, hydrothermal vents punctuate the cold with jets of superheated mineral-laden water, where temperatures can exceed 400 degrees Celsius. Here, the rapid mixing of scalding vent fluids with icy seawater creates steep thermal and chemical gradients, fostering unique microhabitats. Life in these extremes is finely tuned. Enzymes are adapted to function at either near freezing or near boiling temperatures, and metabolic processes are optimized for rapid shifts in environmental conditions. Salinity in the deep ocean remains remarkably constant, averaging around 35 parts per thousand, a testament to the slow global mixing of water masses and the buffering capacity of the ocean. Yet subtle variations in salinity arise from the interplay of ancient evaporation events, the influx of fresh water from melting ice, and the slow diffusion of dissolved salts, creating faint but consequential gradients that influence water density and circulation. These gradients establish invisible boundaries, haloclines and pycnoclines, that affect buoyancy, osmoregulation, and the spatial distribution of species, often separating communities by mere centimeters of water. Oxygen availability is another critical factor, with many deep-sea regions suffering from chronic hypoxia due to sluggish water circulation and limited photosynthetic input. In oxygen minimum zones, concentrations can fall to near zero, compelling organisms to evolve highly efficient respiratory pigments, slow metabolisms, or to abandon oxygen altogether, relying on chemosynthesis or anaerobic metabolic pathways to extract energy from inorganic compounds. The chemistry of the deep is further enriched by dissolved minerals and gases, sourced from both the slow weathering of rocks and the dramatic emissions of hydrothermal vents. Vents release plumes saturated with hydrogen sulfide, methane, iron, manganese, and trace metals, creating chemically distinct oases that support entire ecosystems based on chemosynthetic primary production. Away from vents, the slow descent of marine snow, organic detritus from the upper ocean, provides a steady, if sparse, supply of nutrients. As these particles sink, they are chemically transformed by microbial activity and the surrounding water, altering their nutritional value and availability. The interplay of pressure, temperature, salinity, and chemical gradients generates a dynamic, stratified environment, where even minor shifts can have profound effects on the distribution and survival of life. Each of these elemental forces shapes the physiology, behavior, and evolutionary trajectory of deep-sea organisms, driving the emergence of extraordinary adaptations and life strategies. In the deep ocean, survival is a relentless negotiation with the elemental forces of chemistry and physics, a testament to the ingenuity of evolution and the boundless resilience of life under the most extreme and unforgiving conditions on our planet. In the perpetual twilight of the deep ocean, survival is a matter of molecular precision. Here, the most formidable barrier is not the absence of light or the scarcity of food, but the relentless, all-encompassing force of hydrostatic pressure. At depths exceeding 6,000 meters, every square centimeter of a creature's body is subjected to more than 600 times the atmospheric pressure at sea level, a force capable of crushing steel and shattering glass. For the denizens of the abyss, resisting this invisible weight has driven the evolution of some of nature's most extraordinary adaptations. At the cellular level, deep-sea organisms possess membranes uniquely composed of unsaturated and polyunsaturated fatty acids. This molecular flexibility prevents their cells from becoming rigid and brittle under intense compression, preserving the delicate balance required for nutrient transport and signal transmission. Proteins and enzymes, the microscopic machines of life, are engineered with subtle but crucial differences: reinforced folding patterns, extra stabilizing bonds, and altered amino acid sequences that resist denaturation. This allows vital biochemical reactions to proceed even as pressure threatens to disrupt molecular structure. Some species, such as the enigmatic amphipods and the hadal snailfish, have evolved to accumulate organic molecules known as piezolators, natural pressure protectants like trimethylamine N-oxide or TMAO. These compounds counteract the destabilizing effects of pressure on proteins, allowing the animal's internal biochemistry to function seamlessly. The concentration of TMAO rises in direct proportion to the depth at which a species lives, a chemical signature of adaptation to the abyss. Even the skeletons and shells of deep-dwelling animals reveal the influence of pressure. Many deep-sea fish are nearly boneless, their skeletons reduced to thin, flexible rods or cartilage. This minimizes internal air spaces and reduces the risk of catastrophic collapse. Invertebrates such as sea cucumbers and jellyfish go further still, replacing rigid structures with gelatinous, water-rich tissues that are nearly incompressible and perfectly matched to the density of the surrounding seawater. These bodies, neither heavy nor buoyant, drift effortlessly in the darkness, immune to the crushing forces that would destroy less adapted forms. Eyes, too, are sculpted by pressure. The retinas of some deep-sea fish are supported by specialized proteins, while their lenses are denser and more spherical, resisting deformation and maintaining focus in the high-pressure gloom. In certain bioluminescent species, photophores, organs that produce light, are shielded by pressure-resistant tissues, ensuring reliable signaling and camouflage in the abyss. Perhaps most remarkable are those organisms that have abandoned air altogether. The deepest living fish, the Mariana snailfish, lacks a swim bladder, the gas-filled organ used by most fish for buoyancy. Instead, it relies on the precise composition of its flesh and the distribution of lipids to maintain position in the water column, sidestepping the fatal consequences of gas compression at depth. These adaptations are not universal, but the result of countless evolutionary experiments, each species navigating the trade-offs imposed by pressure, temperature, and chemistry. Together, they form a living testament to life's capacity for innovation under the most extreme conditions. In the abyss, every heartbeat, every flicker of light is a triumph over the elemental crush, a silent, ongoing battle waged at the very limits of biology. Beneath the crushing blackness of the abyssal plain, a paradox unfolds. In the midst of near-freezing water, rifts in the Earth's crust give birth to hydrothermal vents, submarine geysers that spew scalding, mineral-laden fluids into the frigid ocean. These vents, often found along tectonic boundaries and mid-ocean ridges, are the crucibles of some of the planet's most extraordinary ecosystems. Here, the seafloor is alive with activity. Superheated water, reaching temperatures above 400 degrees Celsius, surges from fissures and chimneys, mingling instantly with the icy seawater. This volatile meeting point creates towering mineral spires, chimneys of black sulfide or shimmering white carbonate, sculpted by the relentless chemistry of the deep. Around these vents, the ocean is transformed from a barren wasteland to an oasis teeming with life. Unlike any other ecosystem on Earth, hydrothermal vent communities are not fueled by sunlight. Instead, their foundation is chemosynthesis, a process by which specialized bacteria harness the chemical energy from hydrogen sulfide and other vent-emitted compounds. These microbes form dense mats, clinging to rock and mineral, converting toxic gases into organic matter with remarkable efficiency. In turn, they become the cornerstone of a complex food web, supporting a dazzling array of unique creatures. Giant tube worms, Riftia pachyptela, are icons of this realm. Lacking mouths or digestive tracts, they survive in symbiosis with chemosynthetic bacteria housed within their tissues. Blood-red plumes absorb dissolved gases from the water, delivering them to their microbial partners in a silent exchange of life. Nearby, vent crabs, blind shrimp, and armored polychaete worms cluster around the thermal flows, each adapted to withstand the searing temperatures and toxic chemistry. The diversity is staggering. Some species, such as the scaly-foot gastropod, have evolved iron sulfide scales for protection, a biological innovation unknown elsewhere. Others, like certain vent shrimp, rely on primitive light sensors to detect the faint glow emitted by the scorching fluids. Even the microbial life is distinct, with entire lineages of archaea and bacteria found nowhere else on the planet. Hydrothermal vents are ephemeral, springing to life with volcanic activity and fading as geological forces shift. Yet, in their brief existence, they drive rapid evolutionary change, creating islands of endemism and adaptation. When vents go dark, their communities are scattered, but the genetic legacy of survival endures, ready to colonize new eruptions. These fiery oases offer profound insights, not only into the resilience and inventiveness of life on Earth, but also into the potential for life beyond our planet. The independence from sunlight, reliance on chemical energy, and the presence of extremophiles suggest that, in the darkness of other worlds, life may find a way. In the abyssal gloom, hydrothermal vents are beacons of possibility, a testament to life's ability to flourish against all odds, forged by the very fires that shape the Earth's hidden heart. Far beneath the restless surface, where sunlight never penetrates, an ancient rhythm pulses through the abyss. Here, in the perpetual night of the deep sea, countless creatures embark on migrations as dramatic as any found on land or in the skies above. These journeys, silent and unseen, are orchestrated by the subtle cues of temperature, pressure, and the eternal ebb and flow of the tides. Every night, as the world above slips into darkness, a vast migration unfolds. Billions of organisms, from tiny zooplankton to lanternfish and squid, rise from the shadowy depths toward the surface in search of food. This phenomenon, known as diel vertical migration, is the largest animal migration on Earth by biomass, yet it passes unnoticed by human eyes. For these travelers, the cover of darkness offers safety from predators, while the upper waters promise a fleeting bounty of nutrients. But not all migrations follow the daily cycle. Some species, like the enigmatic gulper eel or the six-gill shark, undertake seasonal or even lifetime journeys, traversing vast distances across the ocean floor or ascending and descending the water column in response to shifting currents and changing temperatures. These odysseys are guided not by sight but by finely tuned senses, detecting gradients in salinity, faint chemical trails, and the pull of deep-sea currents invisible to all but those who call this realm home. Along mid-ocean ridges and in the vicinity of hydrothermal vents, vent-endemic species such as tube worms and vent crabs disperse their larvae on journeys of astonishing duration. Buoyed by deep currents, these microscopic explorers drift for months, sometimes years, in search of new vent fields, tiny lifeboats of genetic diversity ready to colonize the next eruption in the ever-changing landscape below. Yet, migration in the deep is fraught with peril. Food is scarce, and the pressure is relentless. To survive, deep-sea travelers have evolved extraordinary adaptations, gelatinous bodies that withstand crushing depths, metabolic rates that conserve precious energy, and bioluminescent signals that guide the way through utter blackness. Some, like the vampire squid, possess the ability to hover motionless for hours, conserving energy until the time is right to move. These journeys knit the deep ocean into a living web, connecting distant habitats, cycling nutrients, and shaping the very fabric of life below. In the silence of the abyss, migration is both a necessity and a marvel, a testament to the resilience and ingenuity of the creatures that navigate the world's last great frontier. Beneath the crushing silence of the deep, where ancient waters have flowed undisturbed for millennia, a new and invisible force is beginning to reshape the abyss. Climate change. While the deep ocean once seemed immune to the fluctuations of the world above, mounting scientific evidence reveals that its vast cold expanses are not beyond the reach of a warming planet. The impacts begin with the most fundamental element, temperature. As global surface waters absorb more heat, subtle but persistent changes ripple downward. Even a fraction of a degree increase can disrupt the delicate thermal gradients that govern deep-sea currents. These shifts alter the movement of vital nutrients and oxygen, affecting everything from the distribution of microscopic plankton to the migrations of ancient cephalopods. Oxygen, the lifeblood of all marine life, is declining in many deep zones. Warmer waters hold less dissolved oxygen, creating expanding regions known as oxygen minimum zones. Here, only the hardiest organisms survive, while others are pushed to the brink, their ranges shrinking as habitable territory vanishes. The deep's slow pace magnifies these effects. What takes years to change in surface waters can linger for centuries below, leaving ecosystems struggling to adapt. Acidification, too, seeps inexorably into the abyss. As the ocean absorbs more carbon dioxide from the atmosphere, its chemistry shifts, lowering pH and altering the balance of life. Shell-building creatures, deep-sea corals, foraminifera, and countless others, find it harder to construct their protective skeletons. Ancient coral gardens, some thousands of years old, are now threatened by dissolution, their intricate frameworks weakening in waters that have turned subtly corrosive. Nutrient flows are changing as well. Altered currents and stratification can trap nutrients closer to the surface, starving the deep of the organic matter that rains down from above. The famous marine snow, a vital food source for deep dwellers, becomes less reliable, forcing organisms to adapt to ever scarcer resources. The consequences ripple through the food web. Some species respond with remarkable resilience, altering their metabolism or shifting their ranges. Others, finely tuned to a stable environment, face decline or extinction. The balance of life at hydrothermal vents, cold seeps, and abyssal plains is being rewritten by forces set in motion far above their world. Yet the deep ocean remains a place of extraordinary mystery. Its vastness and inaccessibility mean that much of this transformation is unfolding unseen, its full consequences yet unknown. But the evidence is clear. The abyss is changing. And as the deep responds, so too may the entire planet. For the ocean is not just a victim of climate change, it is a powerful driver of Earth's climate system itself. Here, in the planet's last refuge of darkness, the story of climate change is still being written. Silently, relentlessly, and with profound implications for all life on Earth. Far below the rolling plains of the abyssal seafloor, the world plunges even deeper into narrow, winding chasms known as deep-sea trenches. These are the planet's ultimate depths, where the seafloor buckles and folds under tectonic forces, creating gashes that descend over 11,000 meters into the darkness. Trenches like the Mariana, Tonga, and Kermadec are not mere depressions, but dynamic geological frontiers, zones of subduction where Earth's crust is recycled back into the mantle. For decades, these trenches remained impenetrable mysteries. Their crushing pressures and absolute darkness defeated early exploration, leaving only faint hints of their existence gleaned from seismic echoes and the occasional dredged-up creature. It was not until the age of deep-diving submersibles and remote-operated vehicles that the true nature of the trenches began to emerge. Modern expeditions reveal landscapes unlike any other on Earth. Steep, muddy slopes festooned with fields of chemosynthetic bacteria, pools of brine heavier than the surrounding seawater, and scattered oases where life clings to the margins. Here, amphipods, tiny shrimp-like scavengers, scuttle across the sediment, while translucent snailfish glide through the water, their bodies adapted to withstand pressures over 1,000 times greater than at the surface. The study of these trenches is a feat of science and engineering. Custom-built landers, equipped with titanium housings and pressure-resistant electronics, descend for hours before settling gently on the trench floor. They carry cameras, temperature probes, and samplers to capture both the environment and the elusive organisms that call it home. Each mission is a high-stakes venture. Equipment must survive crushing forces, corrosive brines, and the long, silent wait in the dark. The discoveries are profound. Microbes living in the sediments are found to metabolize chemicals from rock and water, hinting at life's potential even on other worlds. Organic matter raining down from above accumulates in these trenches, making them crucial sites for the long-term storage of carbon. Meanwhile, the unique fauna, many species found nowhere else, offer clues to how life can adapt to the most extreme conditions. Yet these frontiers remain largely unexplored. Less than a handful of humans have visited the deepest points, and much of what lies within the trench walls is still beyond our reach. The mysteries of the trenches, how they influence global cycles, what forms of life persist in their depths, and what secrets they hold about Earth's history, continue to challenge and inspire. In the silent, crushing dark, the world's deepest secrets wait, undiscovered, at the edge of human knowledge. In the abyssal world, where light cannot reach and sound travels too slowly to be useful, life has evolved its own language. A silent, invisible network of chemical signals. Here, amid the perpetual darkness and crushing pressure, chemical communication is the currency of survival. Every movement, every interaction, is guided by invisible plumes and trails that drift on the slow, cold currents. For many deep-sea dwellers, sight and sound are unreliable. Instead, they rely on an ancient sensory ability, chemoreception. Tiny amphipods and isopods detect faint traces of organic molecules, guiding them towards a distant meal or away from lurking danger. Even the most subtle whiff of decaying matter, a single molecule in a million, can trigger a feeding frenzy, drawing scavengers from across the barren plains. Predators exploit this chemical web for both attack and defense. The deep-sea hagfish, for example, releases clouds of mucus laced with repellent proteins, deterring larger hunters with a chemical barrier. Some squid and octopus species deploy ink infused with bioactive compounds, confusing attackers not just visually but chemically, masking their scent as they vanish into the black. The art of attraction is equally sophisticated. In the absence of color and light, many species use pheromones to find mates across vast distances. Female deep-sea anglerfish emit complex chemical bouquets, their signatures drifting through the water, guiding males through the labyrinth of the deep. When a male detects the trail, he follows it relentlessly, sometimes for days, until he finds his mate, an encounter that may only come once in a lifetime. In the world of the deep, even cooperation is mediated by chemistry. Colonies of tube worms and mussels at hydrothermal vents release chemical cues that signal the presence of symbiotic bacteria, inviting new settlers to join the community. Some species synchronize their activities, spawning, feeding, or migrating, using chemical signals that ripple through populations like an unseen tide. These molecular messages are fleeting, shaped by the slow churn of the water and the ever-present pressure. They can be as simple as a single amino acid or as intricate as a cocktail of dozens of compounds, each tailored to a specific purpose, a precise moment in the life of the abyss. In this realm, communication is a dance of molecules, a secret conversation that shapes every life and every encounter. It is a reminder that, even in the loneliest places on Earth, the language of life endures, written not in words or light, but in the silent ink of chemistry, drifting through the endless dark.